Hey everyone, and welcome to today's Explainer. We've got an incredibly cool topic today. We're diving deep into the fascinating, high-stakes intersection of artificial intelligence and, well, one of the most chaotic systems on our entire planet, the weather. We're going to look specifically at how NVIDIA Earth-2 is totally revolutionizing the way we predict climate systems by using generative AI. It's a massive leap forward from traditional forecasting, bringing a level of precision and speed that we literally have never seen before. All right, here's our roadmap for the data's journey today. First up, generative AI meets weather. Second, removing noise with diffusion. Third, ERF5 and the data loader. Fourth, training with Physics-Nemo. And finally, high-speed weather inference.
Okay, let's dive right into this. Section 1, Generative AI meets weather. So, when we talk about AI and weather forecasting, honestly, the sheer scale of the math involved can be completely overwhelming. That's exactly where NVIDIA's Physics-Nemo comes in. It's an open-source toolkit that basically saves you from massive headaches. But you might be wondering, why use generative methods at all for weather modeling? Well, older, non-generative AI methods, like your standard regression models, have a pretty major flaw. They tend to blur the output. And, when you're trying to predict a highly specific local storm, a blurry forecast just isn't going to cut it. Generative AI, on the other hand, models chaotic systems probabilistically. It doesn't just guess a middle-of-the-road average, it predicts possible realities. This is absolutely crucial because it allows the model to produce the super fine-scale details required for a process called downscaling, essentially turning a coarse, pixelated forecast into a highly detailed, localized prediction.
Moving on to Section 2, removing noise with diffusion. To actually achieve these hyper-detailed forecasts, the systems rely on a very specific type of generative AI. You've likely heard of them because they're the exact same models that made modern AI image generators suddenly so powerful for everyday use. Let's talk about diffusion models. By definition, a diffusion model is an AI trained to learn a data distribution and generate new samples from it by progressively adding and then removing noise. To understand this simply, think about the static on an old television set or a radio trying to tune in to a clear station. Diffusion models are essentially the grandmasters of tuning out that static to reveal a crystal clear picture hidden underneath. The whole theory here is built on a two-step dance. Step 1 is the forward process. During training, the system takes a perfectly good, high-resolution weather data sample and gradually adds pure noise to it. It effectively destroys the image until it looks like 100% pure static. Then comes Step 2, the reverse process. The AI is trained to recognize that specific static and learns how to filter it out step by step. Eventually, it gets so incredibly good at this reverse process that it can take a field of pure randomized mathematical noise, condition it with low-resolution weather inputs, and completely transform it into a realistic, high-resolution weather state. It's almost like magic, but it's just really good math.
Which brings us to Section 3, ERA5 and the data loader.
Now, what's really interesting about this slide is how we apply all this theoretical diffusion magic to actual real-world data. We need to feed the AI, right? The goal here is basically to build a 10x zoom lens for our weather models. For our demonstration pipeline, we look at two specific data sets. On one side, we have ERA5. This is our low-resolution data source. It's global, it updates hourly, but its spatial resolution is pretty coarse, about a quarter degree. On the flip side, we have DANARA. This is a regional atmospheric analysis from the Danish Meteorological Institute. DANARA is beautifully high resolution, down to 2.5 kilometers, but it's only available in 3-hour intervals. So our goal is to train the model to emulate that high-resolution DANARA target state based on the low-resolution ERA5 background data. We are literally teaching the AI to bump up our spatial resolution by a factor of 10. To bridge these two very different datasets, we use something called a data loader. Think of it this way. If Physics-Nemo is the heavy machinery on a construction site, the data loader is your custom blueprint. It tells the system exactly what materials to bring to the site. In fact, it's the only component in this entire pipeline that actually requires a custom implementation. It's written as a PyTorch dataset, and what it does is return a dictionary with 2 vital keys for every single timestamp. It returns state, which holds the high-resolution Dan raw data, and background, which holds the low-resolution ERA5 data. All right, let's build Section 4, Training with Physics-Nemo. With our blueprint drafted and our data ready to go, we move into the actual construction phase. This is where we build and train the model using Physics-Nemo and its configuration manager, which is called Hydra. Let's break down the architecture of this training pipeline. You can see here how cleanly Hydra manages the hierarchical configuration. You've got your data loader defining the paths. For the model architecture, you can choose a 5-layer unit or even a diffusion transformer. And what's super cool about using a diffusion transformer with PhysicsNemo is that splitting the geographical domain across multiple GPUs becomes totally straightforward for massive use cases. All of your training hyperparameters are managed cleanly, and the whole shebang kicks off through one simple entry point, train.py.
Now, I want you to pause for a second and just look at this number. Hundreds to thousands. That is the sheer scale of GPU hours required for this kind of training. If you're training a regional model, you're looking at the order of hundreds of GPU hours, which, if you run it in parallel across multiple GPUs, translates to less than 3 days of actual wall clock time. But if you scale up to continental use cases, wow, you're stepping into the realm of thousands of GPU hours. It is an absolutely incredible amount of computational heavy lifting. And finally, Section 5, high-speed weather inference. And this brilliantly illustrates the payoff. Why do we go through all that heavy lifting? Because we are transitioning from days of intense, heavy compute training to lightning-fast execution out in the real world. Once your training is complete, you export your model to NVIDIA Earth-2, which is an open-source Python library for AI weather inference. Now, the magic happens. Remember how our high-resolution Danner data was only available every 3 hours? Well, by applying our trained model to the 1-hourly ERA 5 timestamps, we can actually emulate Danner's high resolution at 1-hour intervals. We've effectively filled in those missing time gaps with high-res predictions. And because Earth-2 handles all the input pipelines, switching your data source, say testing the model on completely different systems like GFS or IFS, is literally just a 1-line code change. And the speed post-training, it is genuinely staggering. Inference time, meaning the time it takes the AI to look at the current low-res weather and spit out the high-res forecast, happens in the range of seconds per ensemble member. Let that sink in. Because it's so incredibly fast, running massive ensemble forecasts to generate deeply accurate probabilistic weather models is entirely feasible now. You aren't sitting around reading hours for a supercomputer to run traditional physics simulations. You are getting high-fidelity answers in seconds. So what does this all mean? We've gone from noise and static to high-resolution, localized weather forecasts that generate in a matter of seconds. With AI generating these hyperlocal forecasts so quickly, how will real-time diffusion models completely reshape our response to tomorrow's chaotic weather events? When we no longer have to wait for the forecast, how will our disaster response, our agriculture, and really, our daily lives adapt to an era of instant climate science? It's a huge shift. Think about that as you process everything we've covered today. Thank you so much for joining me for this explainer, and I'll catch you next time.